Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss methods of correction for interfering and modifying inputs, and we will take some examples also. So, today we will discuss about the correction of interfering and modifying input, because in the act of measurement, the measurement has to be, ideally the measurement has to be very accurate, and these interfering and modifying inputs, they deviate the act of measurement from the accuracy. So, they erodes the accuracy of the measuring system. So, interfering and modifying signals are not desired at all, right. So, the issue is how to correct, how to get rid of interfering and modifying signals. So, first is inherent insensitivity. We can make the instrument inherently insensitive to these type of signals. Let us say, for example, if there is a magnetic field, normally in the act of measurement we get interference from the frequency of 50 hertz and multiple harmonics of 50 hertz, because 50 hertz is our electrical supply. So, any cable passing nearby the measuring instrument, this will give this spurious input, or the instrument will get spurious input of 50 hertz and multiple of that in many of the cases, not all cases. So, now first method can be, the instrument can be made inherently insensitive to the spurious input, that is interfering or modifying input. For example, temperature modifies the input output relationship. So, what we can do, the scale which we are using, we can use INVAR. INVAR has very low coefficient of expansion with temperature. So, the scale can be made insensitive to the variation in temperature, right. We can use ceramics also. Ceramics are also very low, they are also having very low coefficient of expansion with respect to temperature. So, the first method is to make instrument inherently insensitive to the modifying or interfering input. Sometimes it is possible, sometimes it is not possible. Another method can be method of high gain feedback. Using this method also, we can get rid of interfering and modifying input. Suppose we have to measure certain voltage. So, where voltage can be measured with the help of a voltmeter, but there are other method also for voltage measurements. For example, there is certain voltage which is applied to a motor. I'll make a block diagram. So, there is motor. So, let us say the relationship is linear, KMO, right, or FMO, because the linear relationship I am writing KMO, and there is input to the motor. The moment this voltage is applied to the motor will start rotating, and it will create torque, not it will start rotating, it will create torque, right. So, the input is given to the motor, it will create torque, and torque will tend to rotate the shaft. Shaft is connected to a spring, right. So, a spring is there, so KSP spring will come into the picture, and the spring will show the displacement. that is how the input signal will be converted. The input signal will be converted to the torque, and the torque ultimately will be converted to the displacement, and you can measure the displacement of a spring, right? So the motor can also be used for measurement of voltage. So this is open loop. Now is in this open loop, it will have, so this is desired input, but it will have interfering input also, and this will also have interfering input. So I will write F M interfering, I M interfering, and I M 2, I M 1, and F, right. So this interference from the spurious source, this will change the output and input relationship, right? It can be interfering input, it can be a modifying input, but it will change input output relationship. Now this problem can be solved. Either we make them inherently insensitive to the spurious input, that is sometime not possible, right? So other method is to have high gain feedback. What we can do, we can apply an amplifier. Before this, we can have one amplifier. So amplifier, right? So amplifier will also have F or K, and this is EI. Now this amplifier will also have some spurious input, so this is also IM3. Right? Amplifier, this input signal will go to the amplifier, then it will go to the motor, then it will go to the spring, and part of this signal will be taken back, and this is a feedback, this is amplifier, this is motor, and this is spring. Now part of the signal will be taken, and this is feedback device. Now feedback device, K feedback, and it will give this to EO. Now this feedback device will also have some spurious input, IM4. I mean, spurious input will come everywhere. I mean, this modifying and interfering input will come everywhere, all the devices. So we have made some feedback system. Now EI minus EO is equal to, and K AM, K MO, K SP, they will be multiplied, right, is equal to EI minus KFB, KF or feedback, okay, KFB XO multiplied by KAM, KMO, KSP. Now what we have done here, EI minus EO, that is the actual input which is going in, because this input XO has, we are getting XO, this XO is again used to convert X into EO, then net input is EI minus EO which is going in, then it is multiplied by KAM, KMO, KS, right, and then so here the input is going which is EI minus EO, KAM, KMO, KS, and this EO is replaced by KFB XO, this is FAM or KM, whatever you want to take, we can take. Now further simplifying this equation, we can write EI, not here, EI KAM KMO KS is equal to 1 plus KMO KSP KFB KAM into XO. This is, we can take XO, right? Now if we further simplify this, we will be getting XO is equal to KAM KMO KSP divided by 1 plus KAM KMO KSP or KFB into EI. If you rearrange this equation, you will be getting this equation. Now here KFB, this KFB feedback is much larger than KAM KMO KSP. So we can always write that XO is equal to 1 by KFB EI. Now what we have done here, we have just simply provided feedback device and just providing feedback device, and this is high gain feedback. By using this high gain feedback, we have reduced the significance of this interfering and modifying input, and our output or the output of the measuring instrument is dependent only on KFB, right? And this is how we can avoid the interference by spurious input to the instrument. So this is another method of high gain feedback which can be used for avoiding the interfering and modifying input. Now third one is output correction. Another way of correcting the output is just calculate how much interference or how much modification of the signal has been done. Some calculations have to be done, and by using those calculations we can correct the output, right? And while sometimes when the programming of the instrument is done, so these type of corrections are added into the programming. For example, if you are using virtual instrumentation, while programming in virtual instrumentation, we can do that, right? So output correction is another method of avoiding interfering and or correcting the interfering and modifying input. Fourth one is signal filtering. We can provide filters, signal filters. Signal filters can be a physical entity or it can be a software also. Now, there are different type of signal filters. One is no pass. This is output and this is frequency. No pass signal. This filter will not allow any frequency to pass. Then another is low pass. So you fix some frequency level and it will only allow the lower frequencies to be passed through the signal, through the filter. Suppose there is an interference of 50 hertz cable. So just provide a low pass filter of 10 hertz. So the filter will allow only frequencies 10 hertz or less than 10 hertz to be passed. So this 50 hertz, the interference from 50 hertz frequency, because this is frequently observed that the passing by cables, they interfere in the act of measurement. So just you provide low pass filter of 10 hertz or 40 hertz frequency, then 50 hertz will be filtered out. And high pass, once we have a low pass, then we can have high pass also. So there is a certain limit. Beyond that limit, the filter will provide frequencies to pass. You just set 100 hertz. So any frequency above 100 hertz will be allowed to allowed, and below that it will not be allowed. So this is known as high pass filters. Then we have band filters. Now band filters are those filters which allow band filters. Which allow only certain range of frequency to pass. Suppose there is a interfering and modifying input at 50 hertz and 100 hertz, right? So you can say that you will allow frequency between 75 to 100 hertz. So that you can avoid the interference from 50 hertz and 100 hertz. So they are known as band filters, which allow a certain band to pass through the filter. And band reject also is also there. The filter which will not allow certain band of frequency to pass through. So there are different type of filters which can be put into the circuit in order to avoid interfering and modifying input. So if we draw the block diagram for filters, so this is interfering, this is modifying input. Modifying input gives input to both interfering and desired. So modifying input, and this is desired input, right? And interference and desired, they will be summed here. This is the normal, this is F interference, F modifying, and F desired. This is a normal arrangement or configuration of a measuring instrument. Now after this, output of desired will go to the filter. They will go to the filter, and after filtering they will combine again. So these filters, they will remove. So this is desired input, output desired, or this is interfering, and this is modifying. This is 0. So modifying is 0 and interfering is also 0, and they will, sorry, this is a plus, and after putting the filters you will get the output which does not carry any impression of interfering and modifying input. So that is how we can use the signal filters for removing the interfering and modifying effect of spurious signals. This is number 5. Method of opposing input. Now if we know the interfering and modifying input, same magnitude and same nature of signals can be put in opposite direction. So they neutralize each other. Now if we look at a mechanical device, let us take example of static pressure probe. Static pressure probe was proposed by Prandtl, and all of you must have used this probe in order to measure the static pressure. So it is a right angle pipe bent at the right angle. right? And the leading edge is the stagnation point. Leading edge is the stagnation point, and it is observed when the free flow, when the free stream passes over this probe, right? The pressure, and static pressure has to be measured from here. There is a hole here, where from you can measure the static pressure, and here we will get the stagnation pressure. So when the flow stream passes over this probe, the velocity here increases, which reduces the static pressure. There are 2 points. One is the nose, where we get stagnation pressure, and another place is there where we measure the static pressure, and there is error incurred because the velocity of the stream is higher than the normal due to intrusion of this tube, static pressure measuring tube, resulting in dip of pressure at this point, right? So how to get the correct static pressure using this tube, because this is a very simple tube and it is very reliable. I mean, this method of pressure measurement is very reliable, but there is an error, and method of opposing input is very useful here, right? First of all, if we draw a pressure diagram, the fluid is coming with a certain velocity v. When it is coming in contact with this tip, what is happening? The pressure of the fluid is rising. So it is half rho v square, right? This is stagnation pressure. Now, but if the fluid, and now if we go in this direction, now at this point the pressure is high, but just after this point, what happens? Just after this point, because normally we confine to ourselves up to this point only, but beyond this point in this plane, what happens? There is a sharp fall in pressure. There is a sharp fall in pressure. There is a sharp fall in pressure due to high velocity of the fluid, right? And high velocity because this has this probe is placed here, and which has increased the velocity of the fluid in the vicinity of the skin of the probe. Now, if farther we move from this point, the pressure will rise. If we are closer to this point, the pressure is high, and when we are moving farther from this point, the pressure is reducing. So we can manipulate the pressure at this opening by controlling length L1. By controlling length L1, we can control the pressure at this point, right? Now the second thing is this column. This is also interrupting the flow, and stagnation point is also generated close to this column. This column is vertical, and fluid is coming on the vertical column. It is also causing stagnation zone, and the pressure is highest at this point, and it will keep on reducing when you are moving away from this point. Stagnation pressure or total pressure. Now this length L1 and L2, they have to be manipulated in such a way that if you sum the pressure at these 2 points, it becomes actual pressure at this point. So I am explaining again this phenomena. The fluid is coming with a certain velocity. Here the stagnation point is there, so pressure will rise, but just after this point the pressure will fall sharply. Now this is vertical, I mean tube, and here also stagnation point is formed, the pressure is high, and this pressure will reduce when we move away from this column, so this L2. Just by manipulating L1 and L2, we can have we can have this negative pressure will be neutralized by this positive pressure and we will be getting actual pressure. Now this has to be done by choosing suitable length L1 and L2 for this tube. So this is a very good example for method of opposing input for removing the interfering and modifying input to the measuring instrument. Now another example of this type of arrangement can be seen in orifice meter. In orifice meter is pipe, and pipe across the cross section of the pipe an orifice plate is fixed, and we put a manometer. We put a manometer somewhere starting from somewhere here, and we simply take the difference in the column, right, and this is how we get the pressure drop, and through this pressure drop, just using the Bernoulli's equation, we get the output, mass flow rate. Suppose there is a change in temperature. When there is a change in temperature, or suppose the temperature rises, when there is a rise in temperature, the density of the fluid will density of the fluid will reduce, and that will change the mass flow rate through the orifice plate. So this instrument is sensitive to temperature. If there is a variation in temperature, the mass flow rate will also change, right. So in order to cope with this problem, a needle is provided, and so when there is a fall in pressure, so this is a closed entity and this is a bellow type of system, and this is also filled with some fluid. This is also filled with some fluid, right. So when there is a fall in temperature, and this needle can move in this direction, this needle can move in this direction. So when there is a fall in temperature, then density of fluid will increase, right. The density of and this bellow will push the needle in this opening, and it will restrict the opening. The moment it restricts the opening, when there is it can be either way. When there is a change in temperature, when the temperature is a temperature rise or temperature fall, accordingly this bellow will move this needle in this opening, and it will restrict the opening in order to maintain the mass flow rate. Because the density is high, then velocity has to be low. When density of the fluid is high, velocity has to be low, and when the density is low, when the temperature rises, density is low, then velocity has to be high, right. So accordingly this needle moves in this opening and restrict the opening in order to maintain the constant mass flow rate. So that is also a method of opposing input. So there are different methods. In addition to this, there can be, it depends upon the designer, we can evolve some more methods to remove the interfering and modifying inputs to the system, but they have to be removed necessarily, otherwise our measurements will not be accurate, and the whole purpose of whole objective of the measurement will be lost. That is all for today. Thank you very much.